Nice. So we're talking about section 2.5 today, limits involving infinity. So a couple of really important functions that we know what they look like. And of course, whenever I give you a function and you don't know what it looks like, you're going to graph it on your calculator, right? You certainly could plot points, but like f of x equals 1 over x is a very important one. And so, right, we want to be able to have a quick sketch of that anytime we talk about it, right? And so we're talking about two kinds of asymptotes here, right? A vertical asymptote and a horizontal asymptote. And we spent lots of time on these in pre-cal, right? So if I have a vertical asymptote, what do I have? I have a denominator that's 0, right? A denominator that's 0 and the numerator that isn't 0, right? So we're really interested in two limits here. We're interested in the limit as x goes to 0 of 1 over x, and the limit as x goes to infinity of 1 over x, right? These two limits we're interested in. And this is what I'm saying. So my limit could be infinity, or my limit could go to infinity, right? So I'm involving infinity in some way in this particular limit. So this one is this one I called the short run for my pre-cal students, right? This is what I called short run behavior, or a vertical asymptote, right? And this one we called long run behavior, or horizontal asymptote, right? Long run behavior, right? So Manish, Alan, right? We talked about those quite a bit last semester. So the notation is a little weird, and I don't necessarily totally agree with it, but we should look at the short runs here first, right? And these are easy enough to get with the graph. So I'm not going to go into all the detail I did in my pre-cal class about that short run behavior. I'm just going to say, looking at the graph, we can see the limit as x goes to 0 from the right of 1 over x equals infinity, right? Positive infinity. And the issue is my limit has to be a real number. So we're going to say right next to this does not exist, right? DNE does not exist. So remember, I need my limits to be numbers, right? And then, of course, the limit as x goes to 0 from the left, right? If you can see where that is going down to negative infinity. So we write negative infinity, but again, does not exist. And so now we can say, in total, the whole thing, the limit as x goes to 0 of 1 over x does not exist. Right? Is that making sense? So just looking at the graph, right, from the right, I see I'm climbing up the hill. From the left, I'm climbing down the hill. So, and I want that distinction of positive infinity or negative infinity first before I go to does not exist. Okay? So we have a theorem for that horizontal asymptote, and the theorem is this, and it's provable by epsilon delta. Okay, the limit as x goes to plus or minus infinity of 1 over x to the n is 0 for n in the natural numbers, right? 1, 2, 3, 4, any positive integer. Actually, it's in yeah, that's good enough. So whenever I see 1 over x or 1 over x squared or 1 over x cubed, etc., right? And you can really see, you can see all of those pictures, right? Just looking at positive infinity, right? there's 1 over x, right? There's 1 over x squared. Oops. Right, so you see that same pattern on that right-hand side that's going to 0, right? This is 1 over x, this is 1 over x squared. So just looking at that moving in the long run toward positive infinity, you can see everything is getting crushed to 0. And it's easy enough numerical too, right? To show this numerically is very simple too, right? 1 over a billion, 1 over a trillion, 1 over a quadrillion, right? 1 over a godzillion, right? It's definitely going to 0. I mean, so easily provable numerically. The epsilon delta changes a little bit, but I'm not gonna bother with it. It's in the book. You can read it if you want. But I'm gonna use that for sure. As we move forward with these. Now, I don't test on this, but it's still something I want you to look at. Okay. So I just want to do a couple of problems here. This is number 15. I have tested on it in the past, so if you see it in an old test, it's because I did test on it. But it's not much I need for going further. This is number 15. The limit as x goes to 1 of 2 minus x over x minus 1 quantity squared. Now, when I teach this in pre-cal, I say, well, f of x kind of looks like 2 minus x over x minus 1 quantity squared, right? But when when I plug in 1, I put the 1 where I can. So I get 1 over 1 minus x minus 1 quantity squared. So you can see I can't put the 1 downstairs, I'd get a 0. But I know at 1, right, this is what I call my short run behavior. At 1, there's a vertical asymptote because my denominator would be 0, right? And it's going to look like 1 over x squared. And of course, you could graph it on your calculator. You don't have to do what I'm doing. You just graph it on your calculator. It'll look like 1 over x squared, right? Do you see the 1 over x squared there coming from that piece? So really close to 1, it looks like 1 over x squared. Far away from 1, it looks like the original function, okay? But since you have your calculators, this is no big deal. But now we're talking about what is this limit, right? So the limit as x goes to 1 from the right of f of x, right? So this original red here. I can look at the graph and see that it's going to infinity, right? So it does not exist. I have to look at the limit as x goes to 1 from the left. And I also get infinity. I can see that both sides are going up. So also does not exist. And from either of those, I could have said right away the limit as x goes to 1 of f of x does not exist, right? So pretty damn simple, yes?
So for this, we just use the
graphical
graph.
Yep. You could do them numerical. You could do them graphical. Graphical's much quicker, which is also why I don't test on it. It's too easy. Nothing to show. 23 is interesting, and there is something we could show here. So I'm going to do this one 2 ways. I'm going to use that theorem I just talked about, and I'm going to use L'Hopital's rule. So this is number 23. It's nice to have a section every now and then where I'm not going to test on it, and it's easy, right? Because they're not all going to be that way. So I've got x cubed plus 5x over 2x cubed minus x squared plus 4. So obviously I'm going for a horizontal asymptote here, right? I'm talking about as x goes to infinity. So in the long run, what does it look like, right? Certainly, again, I could do this graphical. I could do it numerical. But I like to first start with the mother function idea of any function eventually starts to look like its mother, like any human does, or mother or father, or both, right? So star is x cubed plus 5x over 2x cubed minus x squared plus 4 eventually becomes mother over mother in the long run. So this is my pre-cal way of talking about the horizontal asymptote. The numerator is eventually dominated by the x cubed term. The denominator is eventually dominated by the 2x cubed term. So in the long run, right, think about it, if x is $1 billion, who cares about 5 times a billion, right? If I'm taking $1 billion and cubing it, who cares about $5 billion anymore, right? So it's, again, talking about that long run, what takes over, right? And so you can see here that the limit as x goes to infinity of star is the limit as x goes to infinity of x cubed over 2x cubed, which is 1/2, right? So the x cubes just cancel. And this is something to think about. When I have the mother of the numerator and denominator of the same power, the coefficients are going to be my limit there, the horizontal asymptote. So this is a quick way to think about it. This is the way we would think about it in pre-cal before we were doing limits. But it turns out that L'Hopital's rule, right? That L'Hopital's rule, so like if f of c equals 0 equals g of c, right? Then f of x over g of x, the limit as x goes to c, right, gives me 0 over 0, yes? But I can take each function and do a reciprocal of them, right? So I could look at 1 over f of c, right, equals 1 over g of c equals infinity, right? If you think about it, if I do a reciprocal of 0, I get positive. I get infinity, positive or negative, it doesn't matter. So I can see that the limit as x goes to c of f of x over g of x equals the limit as x goes to c of 1 over g of x. Notice I also flipped the location, and here I get infinity over infinity. So what is it saying? 0 over 0 is an indeterminate form, ready for L'Hopital's rule. Infinity over infinity is also used for L'Hopital's rule. Okay? So 0 over 0 and infinity over infinity are basically the same thing. So let's go back to this original limit now. The limit as x goes to infinity of x cubed plus 5x over 2x cubed minus x squared plus 4 is the limit as x goes to infinity of the derivative of the top over the derivative of the right bottom function. Yeah, well, you with me? So infinity over infinity is another version of L'Hopital's rule. So what do I get upstairs? Oops. Yeah, I get what, 3x squared plus 5? And downstairs I get what, 6x squared minus 2x. Everyone agree?
Yes.
So I saw that I got infinity over infinity for my first limit. I did my derivatives. I showed you that I was going to do derivatives. And then I'm going to evaluate my limit again. Well, guess what I get? X squared upstairs, x squared downstairs, infinity over infinity. So I'm going to take another hop here, right? I'm going to do the limit as x goes to infinity of 3x squared plus 5 derivative over 6x squared minus 2x derivative, right? Derivative of the numerator, derivative of the denominator. Obviously, on this test, when you do L'Hopital's rule, you're taking shortcuts. So limit as x goes to infinity of what? 6x over 12x minus 2. Looks like I need one more, right? I'm still getting infinity over infinity. So I'm going to take another hop. Limit as x goes to infinity of 6 over 12. I know I'm going to take one more derivative here, so I get again 1/2, right? So much work compared to the pre-cal method of just looking at the ratios. Yeah.
So the beauty in this is that you're just taking whatever function you have, and you just keep applying the dumb shortcut rule to it until you get something with no x, and it's the most simple.
Exactly.
You have your horizontal answer.
In fact, I posted homework 3 on Blackboard, and there's one there from the book with L'Hopital's rule that you have to do. I think two or three applications of L'Hopital's rule. Yeah. So you keep going until you can take the limit.
Yeah, this one's honestly not that bad compared to our definition of limit.
Right. So another version of this same limit is to use this theorem that we had, that 1 over x to the n goes to 0, right? The limit of 1 over x to the n goes to 0. So let's look at this limit one more time here. The limit as x goes to infinity of x cubed plus 5x over 2x cubed minus x squared plus 4. And this is the process that the book uses every time, is this application of this theorem, that 1 over x to the n as x goes to infinity is 0. What I'm going to do is I'm going to work on this inside function. And I'm going to take the highest power of x and divide every term by that highest power. Right? So x cubed is the highest x term. So I'm multiplying by 1 here, right? And so what do I get? I get x cubed over x cubed plus 5x over x cubed all over 2x cubed over x cubed. And you can see what's going to happen. Right? I'm going to get 1 plus 5 over x squared. And remember, x to the n goes to 0, right? So 5 over x squared is going to go to 0. And here I get 2 minus 1 over x plus 4 over x cubed. And you can see each of these pieces, when I let x go to infinity, each of those pieces are going to go to 0, right? So I have now, looking at my limit, I've got the limit as x goes to infinity of star, and I get 1 plus 0 over 2 plus 0 plus 0. I get my 1/2 again. That's the way the book does everything, because they didn't teach L'Hopital's rule yet, right? But L'Hopital's rule is a lot simpler.
Professor, what page in the book is this?
It's 2.5, section 2.5.
Yeah. So also the hospital rule. So
that's 4.5. Yeah, you use it when I tell you to use it. So like on your test, you're going to have a limit. I'm going to tell you to do it with the conjugate and L'Hopital's rule.
Yeah, so we'll know when to do it. But I was just asking, how do we know if we have to use it? Not like if you tell us.
How do you know when you can use it? When you get a 0 over 0 or infinity over infinity.
Okay.
Yep. So there's only one other issue we really have to deal with, and then one interesting problem to try. Okay. So you can see when I have even the mother functions here, when they're the same power, I'm just going to get a ratio, right, of the coefficients. But if I have a dominant power in the numerator or a dominant power in the denominator, I want to think about those, right? So let's look at the limit as x goes to infinity of like x cubed over x. Well, I can already see that I can simplify this function, right, to be x squared, and then that obviously is going to infinity. Right, just thinking about that original x squared function. Where is it going as x goes to the right? Right, it's going up to infinity. So the key here is when the numerator dominates, I have an infinite limit, right? When the denominator dominates, right, like x over x to the fourth, right, I'm going to get something like the limit as x goes to infinity of 1 over x cubed, and that's my theorem already. 1 over x to the n as x goes to infinity is 0, right? So when the denominator dominates, I'm going to get a limit of 0, right? Numerator dominates, right? This one, denominator dominates. Is that making sense at all? And then when we have the same power, we're going to get a ratio of the coefficients.
Yes, makes sense.
So all of these can be done numerically. They can all be done graphically. They could all be done just with this thought of, you know, what's some other function? Where is it in control? They could all be done with L'Hopital's rule, and they all can be done with that one theorem, dividing by the highest power. So we're going to look at one of those real quick. Okay. So this is number 28. Let me do 27. This one's not easy to do with L'Hopital's because I have the chain rules in play. And we're not quite ready for the chain rule. So I've got 9x squared plus x minus 3x. Square root of 9x plus squared minus 3x. So what do you get here? What are you thinking here? What do you think
We can use like the derivative formula.
Well, it's hard to do this derivative because, well, first of all, what do I get when I plug in my x's?
Infinity?
Infinity minus infinity, right? Infinity minus infinity. So there are a few mathematicians in the history of I guess, our world that have discovered there are different sizes of infinity. So infinity minus infinity could sometimes be 0, sometimes it could be something else. So this is an indeterminate form. It's something that we're going to deal with more in Calc 2 than we will here. But what's our thought here? I'm trying to do a limit and there's a radical, what's our thought?
Where is like the inverse from?
Nope. Begins with a C.
Conjugate?
Conjugate. So I'm going to work on this with a conjugate. So I've got 9x squared plus x minus 3x all times the conjugate, right, over itself. So I need square root of 9x squared plus x plus 3x all over itself. So our first thought is to do this conjugate, right, from what I've taught you so far. I see a radical. I can't evaluate the limit. I got to do something. I got to come up with a replacement function, right? It's a little strange to think about infinity minus infinity. But it's certainly not clear. And if you did this graphically, if you did it numerically, you would see it. You'd see a height that's not 0. So what do I get here? Upstairs I get 9x squared plus x minus 9x squared. We agree with that?
Yes.
So, look at what happens here, right? My 9x squareds go away. I get x over square root of 9x squared plus x, all plus 3x. Now this now will give me infinity over infinity, right? Do you see my downstairs now is turned into infinity minus infinity? It's turned into infinity plus infinity. So if I knew the chain rule, I could do this with L'Hopital's, but I don't. I don't know the chain rule yet. Chain rule says if my inside function is not 1, the derivative of my inside function is not 1, I have to use the chain rule. Okay, so I'm not quite ready for this one yet. Some of you might know the chain rule, but wait for me. So on this one, I'm gonna do my highest power of x. What is my highest power of x here?
9x.
Okay, x squared, you would say, right? But where is that x squared? Where does it live?
In the radical.
In the radical, so that x squared is actually what power?
X.
X. So I'm going to divide every term by x. So I get x over x, square root of 9x squared plus x all over x, plus 3x over x. So something simplify there, and the other thing I can do is I can bring that x inside, right? If I bring an x inside the radical, it becomes an x squared. Make sure you agree with me on that. So I get 1 plus square root of 9x squared over x squared plus x over x squared plus 3. So the x over x simplified to 1, 3x over x simplified to 3. I took the x and moved it into the radical, it became an x squared, right? Square root of x squared is x. And so I can simplify some more here. I get 1 over, square root of 9 plus 1 over x plus 3. And now I'm ready to take my limit, because I have that one theorem, right? The limit is x goes to infinity of star is 1 over the square root of 9 plus 0 plus 3. So I get 1 over 6. Crazy. Pretty crazy. So we got a new homework posted, right? Due Monday. Thank you for the name change on the file. Every time I save the file, I put it in a folder, and if I have to rename everything, right? If everyone says Cam Scanner on it, I don't know whose is whose. So by naming your file, it makes it a little bit easier. for me. When you turn in your test on that Friday, right? Same thing. Test 1, chapter 2 test, your name, taking photos of everything. Every page is a new page in the PDF, and you're going to take photos of your formula sheet, right? So I'm thinking 10 problems, so at least 12 pages, right? 10 problems of photos, and then 2 photos of the formula sheet, right? And you should be working on that formula sheet now.
Professor, do we have to take pictures of like scrap paper?
I mean, if you want me to grade it, yes. If you don't want me to grade it, don't put it on.
Okay.
Yeah. I mean, I don't want to see your desk filled with papers and papers, right? I want to see your formula sheet and the page you're working on. So,
yeah, it's just that, so all of this, like, multiplying and stuff like that, or just expanding and stuff, I do it on scrap paper, but I copy the work onto the
that's fine.
actual computer.
That's fine. You can do that.
Yes.
I'm not going to force anybody to do anything drastically different. I don't want you working in a notebook, right? Turning pages in a notebook. I know some of you like to write on a notebook, for that feel. So just work on a closed notebook, Let's do a continuity problem, right? And then I don't want to do anything new today. I'll start chapter 3 Wednesday. So I want to talk about, let's do a continuity problem, and then let's talk about the camera view, okay? So I want to do those 2 things. Let me see if I have a camera view that I like here first. Sorry. Alan, you mind if I show your picture to everybody?
I don't mind.
Oh, thank you. Let me show a picture here. This is from this summer. Oop. And I did this solely for the purpose of being able to show my class what is good and what is not good. And Alan, yours is good, so don't be nervous. Just waiting for the photo to get there. Now Wednesday, so let's see, what is today? So next week is our test, right? So Friday, I can stop my recording now, right? So Friday